This is problem 1-50E. It's on page 46. Compute the stress in member BD shown in figure P1-50 if the applied force is 2,800 pounds. Alright, so we've got the applied force F is 2,800, let's make it 2,800 pounds force. Okay, and we're supposed to find the, so this is the given, find the stress in member BD. Now I'm going to begin with a free body diagram. And let's see, that should be fine. Member BD is here between the two legs. Now this point is actually pinned to ground and this point can roll. What that means is that while there's an applied force F here, there's no reaction force from the ground at this, on this leg on this side. There can be a Y force, so this is point E, let me call this EY. This is point A, so since A is pinned, there can be an AY and an AX. Okay, but other than that, the reactions of the ground, there's only three of them. Now, we can't actually solve for the force in BD unless we take care of the statics problem first. We need the reactions of the ground first, and that's a common theme. Anytime you see a truss like this, you're probably going to have to do the statics, or work the statics problem first. So solve for the reaction forces first, and then attack the stresses in the members. So let's start with this, and let's sum forces in the x direction. Well, if we do that, actually, it would tell us something pretty straightforward. And that is that I've drawn AX in the wrong direction. It would be a negative 2,800 pounds force, right? Because if this structure is static and we've got a force to the right of 2,800 pounds, AX better pull this way at 2,800 pounds in order to support it. If we sum forces in the Y direction, then we'd have AY plus EY, okay? And those are the only loads in the Y direction. Notice that there's no weight given for this truss. There are no forces in the vertical direction. So that's it. Now if we sum moments about A, well, if you sum moments about this point, AY and AX are going to contribute nothing. F will contribute nothing because it passes through A. That means that you just have whatever this length is. It doesn't really matter what this length is. Let's just call the length L from there to there. What that means is L times EY is 0, and that tells you then that EY is 0, and so AY is 0. Now this may seem a little counterintuitive. It's because your intuition is probably expecting there to be some weight here, but it actually makes sense. If you were pulling with this force F and you had just a little bit of angle upward, the whole thing would rise. And that makes sense. So we solve for the reactions. Basically, AX is the only reaction, and we just drew it in the wrong direction. Okay, now, I'll have to take a different free body diagram in order to solve this because I need the force in BD. If you're looking for the force in a particular member, you'll have to cut that member to find it, or you'll have to use a pin on either end of that member in order to find the force in it. So what I'm going to do, really I guess you can look at it any way you want, but let's just say that I take D here. I'm going to leave this member from, let's see, this must have been C up here. I'm going to leave the member from C all the way down to E. Realize that there must be the force in section BD to hold this thing together. There must be a force to the right that's applied, right? Let me get rid of the E so I don't confuse you with EY, which we know is 0. And now there must be a force at C. Now, how do you know the direction of the force at C? Well, could the force at C have any vertical component? Well, this free body diagram has only horizontal components. So if there were any vertical component at C, this member on the right that I've drawn, this leg, would have to accelerate in the vertical direction. That's not the case. It's not doing that. So there must be a force. Now, which direction would this force act? Well, think for a minute. If you were to sum moments about this point, then the member would rotate this way unless the force at C acts that way. Now let's see if that works. If I sum forces here, or excuse me, sum moments here, well then F is pulling this way, FBD is pulling this way, that works. If I sum moments here, F's pulling in a counterclockwise fashion, FC is pulling clockwise, so this thing can be in equilibrium. Now I want to sum moments in order to find the force in BD. That means I should not sum moments about D, because then the force in BD will disappear, it won't be in the equation. So instead, what I'm going to do, just get rid of this, I'm going to sum moments about C, because notice I don't care about the force at C. That doesn't matter. I know the applied force F, I just want FBD. So let's see, if I sum moments about C and I take counterclockwise as positive, well then about C, FBD is going to cause a negative moment. So negative FBD, whatever it is, multiplied by 30 inches. Now where did 30 inches come from? Well, if you look at your diagram, you'll see the dimensions. That's a 30-inch vertical dimension, and the other one here is 15 inches. So it's the same down here. There's 30 inches here, 15 here, despite my drawing not being to scale. So there's the moment arm of the force FBD. Now the force F is causing a positive moment about C. So plus F multiplied by, but its moment arm is going to be the sum of these two, because it's 30 inches plus 15 more inches. So that's 45 inches. And that summation comes out to 0, right? Because the leg is not rotating or not accelerating in an angular fashion. So there's the result. Then FBD can be solved for very easily. All we need is F times 45 over 30. Let me not write the units. You could, I guess I will, but of course they just cancel. It's 45 inches over 30 inches, the units will cancel. So, of course, F we know is 2,800, so I'll just not belabor it, I'll just write it down as 4,200 pounds force. That's the force in section BD. Now that we've got that answer, we just need the area in BD, and that, off to the side they told us that this member has a rectangular cross section. Actually, I think it's on the figure. I don't have the figure in front of me. In any case, it's a height and width thing. It's just a rectangle. So that's 1.30 square inches of area that can take this 4,200 pound force. So now calculating the normal stress in BD, not BC. In BD, we'd have the force in BD divided by the area BD. And so that's just 4,200 pounds force divided by 1.30 square inches, and that is about 32, I can write this, the board's moving too much, 31 psi. So 3,231 psi is the stress in member BD.